Well, hello again. I guess this will be a kind of brief interlude here where I talk about the second aspect of this wave particle duality. In part one, we talked about the idea proposed by Einstein and others that, well, electromagnetic waves also have particle like properties. And this is the part where we will go in the other direction and talk about the subsequent idea that particles like electrons and protons also have wave like properties. So, just a little bit of background here. In 1801, the physicist Jung performed a what's now called a double slit experiment using light, which was then considered to be proven to be indeed a wave. And the idea here is that, well, if light is essentially an electromagnetic field oscillating up and down and sideways and so on. If they come to this double slit, then it can be at some points where the wave emanating from this opening here, for example, is at this point the field might be pointing downwards, but correspondingly the wave emanating from the other hole might be in a phase such that, well, the electromagnetic field then points upwards at this same point. And if you add them together, they sum up to zero. And you have what is called a destructive interference. But then again, in other places, they are in phase, so then they instead increment each other. So, a little bit of background from episode one. Well, we have in 1905, Einstein says electromagnetic waves are also particles in some sense. And that was based on primarily two experiments, black body radiation and photoelectric effect. But then we move on to 1924, and we have this French physicist, Louis de Broglie, who then proposes the idea that elementary particles are, in some sense, waves. I have not checked in detail his precise reasoning. I'm just speculating that in the background you have this atomic model of Bohr where it is assumed that somehow the angular momentum is quantized as the electrons orbit the nucleus. And then how could that be? Well, sorry, a not so bad assumption could be that we're actually dealing with some kind of wave, and wave-like phenomena combined with boundary conditions such as continuity conditions lead to some kind of quantization always. And then based on the formulas which they had previously derived from the light quanta, he comes up with this idea that particles also have some kind of associated wavelength, which is dependent on its mass and velocity. But I presume that at this point in time, the idea that matter was also a wave in some sense, was limited to elementary particles such as electrons. That this wave, what it then might be, is in some sense, at this moment in time, not just some probability wave, but some actual physical wave of some sort. Well, we can have a little bit of a timeline here. As mentioned previously, in 1924, de Broglie postulates matter waves. And based on this idea, pretty soon thereafter, it seems Schrödinger publishes his equation, which is more or less derived from de Broglie's formula for the matter wave. And he applies some differential operators to pop out energy and momentum, and then he formulates an equation. Then in 1927, there's apparently some diffraction experiment proving what they then claim the wave-like property of electrons, which leads to de Broglie being awarded the Nobel Prize in 1929, and in 1933 we have Schrödinger and Dirac getting their medal. I don't know why I'm focusing so much on Nobel Prizes here. It's a good question. And maybe it's part of the programming we've been through here, but I don't know. So then, where are we? Well, what if we now do the double slit experiment again, but with an electron beam instead? Now, these experiments have been performed, and they seem to yield a result resembling something of the following. Now, the strange thing and interesting thing, indeed, is that, well, the intensity of this beam can be lowered to such a degree that it's essentially only at one point in time only one electron moving through. But as they add up, even with that kind of slow projection, in time they seem to pile up in these kind of regions, so that it seems like, yes, we do indeed have some kind of interference pattern where the single electron seems to interfere with itself in some sense. Now, this is a fairly recent published paper demonstrating this with electrons. This is a graphical representation of the results, that as they gradually increase the second slit here, we see an emerging interference pattern. Now, I mean, my opinion about the photon hypothesis was that it's a little bit of a dead end. It doesn't produce any new physics. It's just more or less saying what is the case, and no continuation of it. But on the other hand, the matter wave hypothesis seems to be like more opening Pandora's box, because now we have to interpret what is really going on here. Now, the most popular interpretation, at least for some time, was the so-called Copenhagen interpretation with leading name Niels Bohr, that interprets this matter wave of de Broglie Schrödinger as a probability wave. That means that, go back a little bit, somehow the probability wave of finding the electron in some specific point, it runs through both of these, and then you can have a probability inference, so that the probability of eventually finding the particle here is much higher than here, for example. Much like interference with an actual wave in the or a field in the case of light waves, but here it's instead some probability because it is thought that when you actually measure the electron being somewhere here, then it was there. And then, of course, we have the so-called measurement problem. It's like, what's your justification for taking this single event of actually the the electron ending up on the plate? Why is that special so that you then can say that it was there? Whereas while it is moving here, it's not really anywhere at the moment until we measure it. And what's special about this measuring event? Well, that problem seemed so difficult philosophically to cope with. So we have alternative interpretations, most notably by Max Tegmark, suggesting that we're actually in a multiverse where all these events happen in some universe, and that we're just seeing essentially one trajectory of a multitude of outcomes. But now comes, I guess, the essential point that I want to make, and which is maybe where I can persuade you that we should be looking in another direction. Here we have, well, an article describing the various experiments that have been conducted on electrons and so on. But what they also write here is that this has also been demonstrated with neutrons, atoms, molecules as large as carbon 60 and carbon 70. And then at least I start thinking, well, wait a minute. It was difficult enough to fathom the idea of an electron probability wave propagating in space. But now, if we're having a large molecule and we go back, I mean, are we really to believe that this entire molecule has its own probability wave function that simultaneously propagates through these slits? And that at the other end, at the plate, it somehow appears there intact, without any electrons missing somewhere else or anything like that. Also, I mean, if there's an entire molecule with many electrons, well, why don't we model each single electron as some kind of wave? I mean, how are we really to deal with this? Um, and I don't think that quantum mechanics at the moment deals with it. I have never seen any discussion of this where this arbitrariness between sort of modeling each elementary particle as some kind of wave, and on the other hand, treating the entire molecule, atom, body. I mean, where's the limit? Is that also supposed to be some kind of probability wave? So I will leave it there, but this will be the starting point for my conclusion, which I plan to do in the next episode, where I will propose an idea how this can be resolved, based on another physical property. So hope to see you then. And for now, bye bye.